In this video, I'd like to talk about oxidation reduction reactions. Oxidation reduction reactions are a very important category of chemical reactions in the field of chemistry. They are not actually covered in Chapter 8, but because Chapter 8 is about describing chemical reactions, I thought this would be an important time to introduce it. So let's begin. What does the word oxidation mean? Well, oxidation clearly comes from the word oxygen, and originally oxidation meant reaction with O2, elemental oxygen. So for example, if you've ever seen your car rust, you have seen iron being oxidized by air. Iron reacts with elemental oxygen to form iron 3 oxide. Hey, that equation isn't balanced. Why don't you pause the video right now and see if you can practice balancing equations? Well, I see that oxygen has a subscript of 3 on the product side and a subscript of 2 on the reactant side. The least common multiple of 2 and 3 is 6. That means I'll need a 2 to give me 6 oxygens on the product side, and a 3 to give me 6 oxygens on the reactant side, and then to balance iron, I'll put a 4 there. However, the reverse process also occurs, and that historically has been called a reduction. Many thousands of years ago, people in the Middle East realized that if you take this orangish-brown rock, namely iron oxide, mix it with charcoal, heat the heck out of it, at the bottom of your fire pit, you will see a chunk of solid iron, the mass of which is less than the mass of the iron oxide you started with, hence it was reduced. In this case, iron 3 oxide is being converted to elemental oxygen. And once again, we can balance this by putting a 2 here, a 3 there, a 3 there, and a 4 there. So, in this oxidation process, the first equation, iron is losing electrons. The reaction that occurs is iron atoms are forming iron 3 plus cations with the loss of 3 electrons. In the reduction process, in the second equation, iron is gaining electrons. The iron 3 plus cations are accepting electrons to form iron metal. So, our original definition of oxidation reduction is as follows. Oxidation means loss of electrons. Reduction means a gain of electrons. So if in a chemical reaction an element is losing electrons, we say it's being oxidized. On the other hand, if in a chemical reaction an element is gaining electrons, we say it's being reduced. And an oxidation reduction, or redox reaction, is one in which electrons are being transferred from one element to another. Now, it would be good to have a mnemonic device to help us remember these definitions. Oxidation is a loss of electrons, reduction is a gain of electrons. So to help us come up with a mnemonic device, we have our friend Leo the lion. His name is Leo. And Leo says, grrr. What does that mean? It means loss of electrons is oxidation, and correspondingly gain of electrons is reduction. So there's our original and most narrow definition of oxidation and reduction. But here's a question. Must a redox reaction necessarily involve oxygen? If our definition simply involves gaining or losing electrons, does O2 have to be involved? Well, here's an example. Sodium reacts with chlorine to form sodium chloride. You should be able to write and balance an equation to represent this reaction. Okay? Sodium is a monatomic solid. Chlorine, as elemental chlorine, is a diatomic molecule that occurs in the gas phase. Sodium chloride, I can write the formula knowing the charges on the anions formed, NaCl, and I know that all pure ionic compounds are solid, and I can balance it by putting a 2 before sodium chloride to balance the chlorines, and a 2 before sodium to balance the sodiums. Which element in this reaction is being oxidized and which is being reduced? Well, is an element in this reaction losing electrons and therefore being oxidized? And is there an element in this reaction gaining electrons and therefore being reduced? Well, yes, there is. The sodium atoms are losing electrons to form sodium cations. This represents an oxidation. The chlorine molecules are gaining electrons to form chloride anions. This, therefore, is a reduction. So, anytime you have a reaction in which a metal and a nonmetal combine to form an ionic compound, it's really easy to tell not only that this is an oxidation reduction reaction, but who's being oxidized and who's being reduced. which is what we're trying to answer. The metal loses electrons to form a cation. Therefore, the metal is being oxidized. The nonmetal is gaining electrons to form an anion. Therefore, the nonmetal is being reduced. Now, here's an important question. Must every oxidation involve a reduction and vice versa? The answer clearly is yes. It is not possible to have a reaction in which one element is losing electrons and another element is not gaining them, or vice versa. Now, let's consider the combustion of methane. Every time I light the Bunsen burner in the chemistry lab, this is the chemical reaction that's taking place. Methane, a molecular compound that has the formula CH4, is combining with elemental oxygen to form carbon dioxide gas and water vapor. Now, because I am combining a substance with oxygen and forming oxygenated products, this must be an oxidation-reduction reaction. But these are all molecular compounds and there are no ions formed. So, when there are only nonmetals present, that is, there are no ions, how can we tell which element is losing electrons and therefore is oxidized, and which element is gaining electrons and therefore is being reduced? Well, to answer that question, scientists came up with the concept of oxidation numbers, a model that helps us answer those two questions. An oxidation number is a positive or negative integer that I assign to an element in a formula in a chemical reaction. The oxidation number tells the relative charge on the element compared to the neutral atom in that particular formula. And we will use a change in oxidation number to tell us whether an element is being oxidized or reduced in a particular chemical reaction. So first, let's review the rules for assigning oxidation numbers. Rule number 1, if the atom is present as an uncombined element, meaning the pure element, the oxidation number is 0, which makes sense because if the oxidation number tells the relative charge compared to the neutral atom, if it is the neutral atom, the oxidation number is 0. In a monatomic ion, that is an ion that exists as a single atom with a positive or negative charge, the oxidation number is equal to the charge on that ion. In all compounds, hydrogen has an oxidation number of positive 1. In nearly all compounds, oxygen has an oxidation number of negative 2. There are relatively few exceptions. If there is an exception, I'll tell you. In binary molecular compounds, the more electronegative element has an oxidation number equal to the charge on the anion it commonly forms. It's not an anion because it's a molecular compound, but we're kind of pretending it's an anion. And then finally, the most important rule, in a molecular polyatomic ion, if you add the oxidation numbers of every atom in the formula, it must equal the overall charge on the molecular ion. If it's a molecule, the charge is 0. If it's a polyatomic ion, it's whatever the charge is on the ion. On the next slide, let's look at a series of formulas that we might encounter in a chemical equation and assign oxidation numbers. Chromium is a pure element, therefore its oxidation number is 0. Nitrogen in N2, even though it's a diatomic molecule, it is still a pure uncombined element. Its oxidation number is also 0. CaCl2 is a binary ionic compound that consists of calcium 2+ cations and chloride anions. Rule number 2 says the oxidation number in a monatomic ion is the same as the charge, so calcium will have an oxidation number of +2, chlorine will have an oxidation number of -1. Similarly for aluminum oxide, aluminum exists as cations with a 3 positive charge. The oxide anion has a 2 negative charge. Therefore, aluminum has an oxidation number of +3, oxygen -2. Bromine trifluoride is a binary molecular compound. There are no ions in it, but our rule says in a binary molecular compound, the more electronegative element has an oxidation number equal to the charge on the anion it commonly forms. Fluorine is more electronegative. It commonly forms an anion with a single negative charge. Therefore, the oxidation number on fluorine is -1. To assign the oxidation number on bromine, we will use the final rule, which is that the sum of the oxidation numbers of every atom in the formula must be equal to the overall charge. Because it is a neutral molecule, the overall charge is 0. In order for that to be the case, bromine must have an oxidation number of +3. +3 from bromine plus 3 times -1 from fluorines equals 0, which is the overall charge. In water, we'll use the rules for hydrogen and oxygen. Hydrogen compound has an oxidation number of +1. Oxygen has an oxidation number of -2. And as we can see, they add up to 0, the overall charge on the molecule. H2O2 is hydrogen peroxide, and that's a bit more complicated. Hydrogen can't have any oxidation number other than +1, In this case, oxygen cannot have an oxidation number of -2, otherwise it would not add up to 0. And we can see from algebra, oxygen must have an oxidation number of -1. In this category of molecules called peroxides, oxygen will have an oxidation number of -1 instead of -2. That's an exception to our general rule, and I will always tell you. H2SO3 sulfurous acid, hydrogen has an oxidation number of +1, oxygen has an oxidation number of -3. In order for the sum of the oxidation numbers to be equal to 0, pause the video and think about that for a minute. 3 oxygens with an oxidation number of -3. I'm sorry, that was a mistake, -2. Fix that. 3 oxygens, each with an oxidation number of -2 makes -6. Each of the 2 hydrogens has an oxidation number of +1, which is +2. -6 plus 2 is -4. For the sum to be 0, sulfur must have an oxidation number of +4. In K2SO4, I see a metal, and in fact, this is a compound. I'm going to make my life a little easier by separating this into the potassium cations and the sulfate anions, SO4 with a 2 negative charge. I will use the rule that the oxidation number on an atom in a monatomic ion is equal to the charge in the ion, so each potassium has an oxidation number of +1. I'm now going to zero in on the sulfate anion, SO4 with a 2 negative charge, and use the rule that the sum of the oxidation numbers must be equal to the charge, which in this case is not 0, but -2. Each of the oxygens must have an oxidation number of -2. 4 times -2 is -8. In order for the sum of the oxidation numbers to be -2, the sulfur must have an oxidation number of +6. Finally, NH4Cl, I need to recognize that this consists of the polyatomic cation ammonium, NH4+, and chloride Cl-. Chloride is a monatomic anion. The oxidation number in chlorine is equal to the charge, which is -1. Hydrogen in compounds has an oxidation number of +1. In order for the sum of the oxidation numbers on every atom in the polyatomic cation to be equal to the charge, which is +1, the nitrogen must have an oxidation number of -3. So, now, let's go back and look at our methane combustion reaction, and again, try to use oxidation numbers to answer the question, which element is being oxidized and which is being reduced. First thing I'll do is assign oxidation numbers to all elements. Oxygen in pure oxygen has an oxidation number of 0. Hydrogen +1, oxygen in a compound is -2. In both carbon dioxide and water, oxygen has an oxidation number of -2. In carbon dioxide, in order for the sum of the oxidation numbers to be equal to 0, carbon must have an oxidation number of +4. In methane, CH4, hydrogen has an oxidation number of +1. And for the sum of the oxidation numbers to be equal to 0, the charge on methane, carbon must have an oxidation number of -4. So now, what happened to the oxidation number of carbon? We see that the oxidation number of carbon went from -4 to +4. Its oxidation number increased. An increase in oxidation number corresponds to a partial loss of electrons. Now you may ask yourself, how is this possible? How is going from CH4 to CO2, how does that correspond to a partial loss of electrons? Well, if I look at the carbon-hydrogen bond and the carbon in methane and the carbon-oxygen bond in carbon dioxide, I will see that in methane, hydrogen has a partial positive charge and carbon has a partial negative charge because carbon is slightly more electronegative than hydrogen. But in carbon dioxide, oxygen has a partial negative charge, carbon has a partial positive charge. So in this reaction, the partial charge on the carbon atom is going from negative to positive, corresponding to a partial loss of electrons. Therefore, we say carbon has been oxidized in this reaction. What happened to the oxidation number of oxygen? Let's scroll back up and see. It went from 0 in O2 to -2 in both carbon dioxide and water. So its oxidation number decreased. A decrease in oxidation number means a partial gain of electrons. Once again, I can ask myself, how does this correspond to a gain of electrons? Well, in O2, I have neutral atoms. There is no partial charge, so I'll put a 0 there. But in both carbon dioxide and in water, Oxygen now is bonded to a less electronegative element. It has a partial negative charge, and carbon and hydrogen have partial positive charges because they are less electronegative. Thus, oxygen is reduced in this reaction. Okay? So, here are our new and more general definitions of oxidation and reduction. Oxidation is indicated by an increase in oxidation number on going from reactants to products, which corresponds to a partial or complete loss of electrons. So an element is oxidized if, on going from reactants to products, its oxidation number increases. A reduction, on the other hand, is defined as, or is indicated by a decrease in oxidation number, which corresponds to a partial or complete gain of electrons. And we say an element is reduced in a chemical reaction if, on going from reactants to products, its oxidation number decreases. So, what you should be able to do at this point is to write and balance an equation to describe a chemical reaction. We did that earlier in the unit. Assign oxidation numbers to all elements on each side of the arrow. And then, based on changes in oxidation number, as indicated at the top of the slide, identify which element is being oxidized and which element is being reduced. And then finally, identify the oxidizing agent and the reducing agent. What do those terms mean? Oxidizing agent is defined as the reactant that causes an element to be oxidized. A reducing agent is defined as the reactant that causes an element to be reduced. For example, let's go back to the methane combustion reaction. Which element did we say is being oxidized? We said carbon is oxidized because its oxidation number is going from -4 to +4. An increase in oxidation number corresponds to a partial or complete loss of electrons or oxidation. Which reactant, and by the way, the agents are always on the reactant side, caused carbon to be oxidized? Well, it has to be O2 because O2 contains the element that's being reduced. Which element did we say is being reduced? Oxygen is being reduced because its oxidation number is going from 0 to -2. Which reactant caused it to be reduced? Well, it must have been the reactant that contained the element being oxidized, which is methane. Notice that the oxidizing agent and reducing agent correspond to the complete formula of the substance. So, the oxidizing agent contains the element that's being reduced, and correspondingly the reducing agent contains the element that's being oxidized. On the next slide is a really nice graphic that illustrates that. Here, A is reacting with B. A is giving away 2 electrons to B. B is gaining those electrons from A. Because A is losing electrons, it is being oxidized. Because B is gaining electrons, it is being reduced. B is the oxidizing agent because it is causing A to be oxidized. A is the reducing agent because it is causing B to be reduced. So, let's do a final example. Phosphorus pentafluoride gas reacts with magnesium to form elemental phosphorus and magnesium fluoride. We will write and balance an equation, assign oxidation numbers, and identify which element is being oxidized, which is being reduced, which is the oxidizing agent, and which is the reducing agent. So, phosphorus pentafluoride has the formula PF5. I tell you it's a gas because you have no other way of knowing its physical state. Reacts with magnesium, a pure element. Metals are monatomic solids. To form elemental phosphorus, you have in your notes that the most common form of elemental phosphorus is a tetratomic molecule, P4, which is a solid, and magnesium fluoride. Magnesium forms a cation with a 2+ charge. The fluoride anion has a single negative charge. So our formula of magnesium fluoride is MgF2, and you have in your notes that pure ionic compounds are always solid. Let's see. To balance this equation, I'm going to save magnesium for last. And I think I'm going to start by balancing phosphorus, and I'll do that by putting a 4 before the PF5. That balances phosphorus. That gives me a total of 20 fluorine atoms on the reactant side. So to get 20 fluorine atoms on the product side, I will need a coefficient of 10 before magnesium fluoride. To finish up, I have 10 magnesium atoms on the product side. To get 10 magnesium atoms on the reactant side, I will put a 10 here. We'll assign oxidation numbers. Phosphorus on the reactant side, well, let's start with the easy ones. Let's start with the pure elements. Magnesium and phosphorus are uncombined elements, so we'll give them oxidation numbers of 0. We said magnesium on the product side, and magnesium fluoride exists as a monatomic cation with a 2+ charge, therefore its oxidation number is +2. Likewise, fluorine has an oxidation number of -1. In the reactant side, phosphorus pentafluoride is a binary molecular compound. Fluorine, the more electronegative element, takes an oxidation number equal to the charge on the anion it usually forms, which is -1. And for the sum of the oxidation numbers to equal 0, phosphorus must have an oxidation number of +5. So now, who is being oxidized? Oxidation is defined as an increase in oxidation number. Clearly, the element being oxidized is magnesium. Magnesium is oxidized because its oxidation number is going from 0 to +2. Reduction is defined as a decrease in oxidation number. Which element's oxidation number is decreasing? It must be phosphorus. So phosphorus is reduced because its oxidation number is going from +5 to 0. The oxidizing agent is the reactant that is causing magnesium to be oxidized. That must be phosphorus pentafluoride. And that is because it contains phosphorus, which is the element being reduced. Phosphorus is being reduced, therefore magnesium must be the reducing agent because it contains magnesium, the element being oxidized. Okay, so that's our summary of oxidation reduction reactions, and in the next unit, in this next section of this unit, we will learn about other categories of chemical reactions. See you then.